I was thinking when I came here, I did not intend to make any talk. I was thinking I could sit here, sit in the conference and relax and enjoy the fantastic talks. But I got an email from Alexander and he said, would you like to give a talk for two purposes? One is dedicated to Professor Jim Wright's 85th birthday, and another one is dedicated to a good colleague, Mark Lucky. I said yes, immediately. So I'm very happy to come here to especially to give a talk in this special event station, as I said, dedicated to Professor Tim Rice and to Dr. Makuraki. I was I had my first sabbatical in 2000 and 2001 at Harvard in John Hutchinson and Mr. Vanessa. I did not have contact collaboration with Professor Tim Rice, but I followed his one of his courses, and I also talked to him a few times in his office. I think, as Alexander said, I think Jim Rice is not only a giant in fraction mechanics, he's a giant in mechanics in general. So I think I got a lot of inspiration from him until today. And Mark Racking, I think it was when I was in the States, first time on my sabbatical in Harvard, I got contact with Marco, and he wrote to me that he was interested in having a copy of my complete Gurson UMAT code. And at that time I already distributed freely to the world, and I was very happy to give a copy to Mark Lucky. And it turned out that Mark was one of the few colleagues who really understand the essence of complete Gurson model. And I think he was one of the promoters of complete Gurson model. I was very happy for that. And today I was very happy to see Mark's family. Okay, that was the introduction. Today I will talk some insights into the micromechanical modeling of ductile fracture. This is my overview. So first, I will talk micromechanical modeling of ductile fracture. And especially I will mention the cell model analysis, which provide the ground truth data for benchmarking and for calibrating of analytical equations. Then I will mention one of the most popular models in ductile fracture, the GTN model. I think most of you have heard about GTN model. And I will mention two weaknesses of GTN model. First is incompleteness. Second one is non-uniqueness. These are related together. And then I will briefly bring you to the complete Gurson model, which I named it maybe more than 30 years ago. And then I will talk about the CSM, complete Gurson model strategy for parameter identification. That's to identify, to have a model is one thing, to have parameters is another thing. So we have to have a good strategy to identify the parameters. And then I will talk one unexplored application about of the complete Gurson model. Then some takeaways. Okay, so how do you know how we teach fracture mechanics today? When we teach fracture mechanics, first we tell the students that there is a corrective stress field, right? This field is controlled by one parameter, either J integral, every time I talked about that's from Jim Rice, and I or controlled by CTUD. Okay. So sooner, several weeks later, we'll tell the students that that's not true indeed. I mean, corrective stress field is not controlled by one single parameter. It's controlled by maybe another parameter. We will have T squared or Q squared. So here we will have what I have plotted here that I mean corrective stress field may be controlled by TZ. Professor Guan has a fantastic talk today about the TZ constraint parameter. But in general, what we are telling that the fracture toughness is not a constant. It depends on the corrective. Fracture toughness depends on the corrective constraint. Okay, transferability is a challenge. We cannot do the transfer. We cannot transfer from one geometry to another one. That's a challenge. And then what we can see, what we can demonstrate is that micromechanical modeling could offer alternative transferability. That's my starting point. I will end the transferability of my talk. Okay? Then what is micromechanical modeling? Micromechanical modeling is a kind of physics-based approach used to predict the macroscopic properties based on local properties and microstructural features. So if you look at the specimen on the left, and we could easily identify a kind of unit cell model. Here I have a unit cell model in the center, and I have 4 keywords. First is there should be a periodicity. That means we can repeat this unit cell model. And at the bottom, there is an approximation. I mean, it's always approximate of the microstructure. I mean, microstructure is always more complicated than the model itself. And then with the unit cell, we can study the morphology that includes the size, shape, distribution of these faces, and the morphology and local properties on the right, on the macroscopic behavior. So we have on the right hand side we have ground truth data. That is a kind of data we can use for benchmarking analytic results. For example, benchmarking the Gurson model and the GTN model. We can use AI to identify the critical microstructure which can realize the optimal performance. So this is going to be the optimal microstructure, and so these things we can do with micromechanical modeling. Okay, let's look on ductile fracture. That's my talk. Ductile fracture is kind of a field which is massive. I mean, everyone has heard about this. I mean, it's a lot of studies already have been carried out. So ductile fracture mechanism, we know it's if you look at the fracture surface, there are a lot of dimples. So we have three stages of ductile fracture mechanism. We have void nucleation, and that's from the particles through particle fracture or particle debonding to the matrix. And we have, this nucleation is could be stress-strain controlled. We could have a plasticity induced vacancies that could nucleate the void. This is very exciting for the hydrogen embrittlement which we are working now. And then once the voids have been nucleated, then these voids have under the plastic deformation and stress reactivity, hydrostatic stress, these voids will grow. So, I mean, then at certain stages, the void glow will be stopped. So we will have void failure. That's also called a coalescence of plastic localization by void necking or, I mean, sheeting. Here we have two type of loading. One is tensile, another shear. And in this talk, we will focus on tensile loading. My question is, can you guess, is void coalescence stress controlled or strain controlled? This is, I will ask you later. So let's talk about cell model. So for ductile fluctuation, we can easily identify a two-phase cell model. I mean, one phase is a matrix material. That's easily we can understand. Another phase is empty, nothing. So it's we have a hole inside. This is a very typical phase cell model for for the ductile fracture. If we make cell model analysis, that means we can carry out numerical analysis of this cell model. What we need to have input. We will have the matrix property. That's sigma 0, that's yield stress and hardening, right? Sigma 0 and n, these are the matrix material property. Okay? Then we can have a kind of F0, that's initial volume fraction. That's the only input we need. And then we apply a load to this cell model. Then we will have output here. On the right hand side is output. We will have deformation and fracture. That means this cell model can automatically, in fact, we can use the word autonomously, controls deformation and fracture. Deformation, that's a homogeneous plastic flow, and the fracture, that's a localized plastic flow. So that means cell model can reveal both the deformation and the fracture. That's important. And that means it's complete. Cell model is complete. That means it can reveal both deformation and fracture. Okay, this is completeness. Then cell model is also unique. If we try different void volume fraction, on the left you have yellow, and you have red and purple and green. So different F0, then you will get different ductility, right? So this is unique. There is a one-to-one relation between the initial void volume fraction and ductility. That's important. So for cell model analysis, we have both the completeness and the uniqueness. What about the model, analytical model? Let's take all these models available. So we have, everyone knows about von Mises model, I mean, sitting here. Von Mises model could be regarded as a kind of micromechanical model as well. So let's start with the von Mises model. Von Mises model is a kind of yield function, right? There is no inherent failure criteria. You can use the von Mises model to analyze the problem, but it can yield. It cannot fail. That's important message. Then let's look at the Rice-Tracy model. I mean, here Professor Rice again. It's a very famous model. And if you think about, we have infinitely large plastic domain. Inside we have a very small void. And under the plastic deformation and hydrostatic stress applied, then we will have void expansion. So Rice-Tracy model can calculate the R dot over R. This is interesting. I mean, but there is no inherent failure criteria. That means you can probably use a kind of critical value for this expansion, but you cannot predict the failure. Then let's go to Gurson model. Gurson shrink the infinite large media to a finite media. Okay, then you have a void volume fraction instead of void radius. So you have V, V cell over a V and void over V cell. So you have F, and you have a yield function as well. And this yield function is interesting. Gerson's yield function considers the effect of void volume fraction. That means if you have a large void volume fraction, it's easy to yield. If you have a low volume fraction, it's difficult to yield. And it's kind of you can Gerson model can calculate the void growth. So it's a yield function itself, but it can consider the void growth model. But unfortunately, there is no inherent criteria as well. So then let's go back to the most famous model, GTN model. GTN model, I mean, after the work of Tverbgard and Needleman, Gurson model becomes quite capable. GTN becomes quite capable model. It can consider the void nucleation. So we could have a cluster nucleation, we could have a continuous nucleation, we could have a statistical nucleation. It could be stress controlled, it could be strain controlled. Okay? And then we could have void growth. Void growth is the Gurson model, so it's already there. Then GTN model could consider void failure. But it provides a framework for considering void failure. But there is it needs FC, it needs the critical void volume fraction. There is no inherent criteria. Maybe it's confusing, but let me explain a little bit more. So FC indeed it was assumed by Tverbgard as a constant, Tverbgard-Needleman, but it turned out that it's not constant. I used the Copernic-Needleman data and I found that the FC depends on the structural activity, depends on the initial void volume fraction. That means it's not correct to assume FC is a constant. So my conclusion is that GTN can model void nucleation, can predict the void growth, but unable to predict the void failure. So it's not complete. There is incompleteness problem. And because of this incompleteness problem, then there is another problem called the non-uniqueness problem. For notchless specimen, you can find the infinitely number of sets from F0, FC sets, which give identical or almost identical curve. So in fact, you can have a kind of equation. FC will be equal to a function of F0. That means the problem is that different initial conditions can lead to same ductility. That's a problem. So because of this weakness of the GTN, I think that was around 30 years ago. I was inspired by Thomason's work. I tried to incorporate Thomason's Gurson model into Gurson. So because ductile fracture is a complete ductile fracture model should include both the void growth, nucleation growth, and Gurson. So GTN is not complete because it cannot predict the void failure. So in GTN, because Gurson is simulated by an arbitrary and negotiable FC. So by incorporating GTN with the physical Gurson model, then we get the so-called complete Gurson model. Complete Gurson model is not only one, it could be many. So here is a kind of illustration. So we have x-axis is equivalent plastic strength, y-axis is maximum principal strength. So black curve is a kind of GTN curve. And then we add one additional mode, deformation mode. That's called localized deformation mode. This localized deformation mode is not working until these two curves cross each other. So in the beginning, it's not possible to have localized deformation until one void are large enough. Then you could have localized deformation. Okay. And then we can have analysis of the parameters involved in CGM. So CGM, we have yield stress, sigma zero, Young's modulus, that's given, and Poisson ratio, that's given, and plastic strength, that's also given. Then we have Q1, Q2, and Q3, that's 12 logarithm parameter. In principle, these can be fitted very nicely as a function of n hardening. So I mean, with machine learning technique, we can have a perfect fitting of these. And then we have FC, that's not a constant. FC determined automatically. Then FF, can be determined set to zero point 0.2. I mean, Benzaga and Leblanc has a lot of data on that. Then we have FQ, that can be determined. So the only parameter left without determination, that's the nucleation parameter. So we can use single specimen strategy or multi-specimen strategy to determine to fit the nucleation parameter. So because nucleation parameter is the only parameter which needs to be determined. It links to the material failure one-to-one by one-to-one relation. So here are the strategies to fit. If we use one single specimen, then we can, for example, make different calculations with the void volume fraction, initial void volume fraction. Then we get one fits the experiment very well. Then if we use multi-specimen strategy, then we can fit that ability. So these are the so we can use different integration model. If the cluster model is not working, then we can use the continuous model. And if the continuous model is not working, then we can use the statistical model. So my advice is that try a simple model first. And then this is my last one of the last slides. Transferability, I mean, we should have a resistance curve. I mean, we could have JR from fraction mechanics specimen and to the component. But in fact, due to the constraint, this is not working. So this is not working. Then we can have transferability by void nucleation parameter and plus a kind of length parameter, characteristic length parameter, LC. That's the way of transfer from small specimen in the laboratory and to the large components in service condition. So we have to have both low stress gradient specimen and high stress gradient specimen. Okay. Another unexplored application is, I mean, we know that we have a high strength steel, low strength steel, medium strength steel. But have we heard about high strength steel, but high ductility steel, low ductility steel? So you have never heard about this, but it's very much needed. So we have a ductility is horizontal, strength is vertical. So we could use the nucleation parameter to classify material, classify the steel by this way. So this we could have low ductility steel and high ductility steel. So this is possible. Okay, this is my last slide. Void nucleation is the root cause, is the thing of is the original thing of ductile fracture. Void quiescence is stress control. I mean, that may be surprising to many. I mean, GTN is not complete, has a non-uniqueness problem. CGM, complete Gurson model, links the ductile flucture to FN. FN, that's nucleation parameter. And F0 is not the same as volume fraction of particles. I mean, we have Franklin's equation for calculating the volume fraction of particles, but I think it's not the same. And Fn, the nucleation parameter, can be inversely determined. Fn can be maybe used for classification of ductility, and maybe can be used for unifying brittle and ductile fracture. That's what we are working. And my last message is the fewer the parameter, the better. Not obvious. Yes, thank you.